When my students first hear about the problem of induction, something I tell them about after sort of laying out some of the aspects of the process of scientific inquiry and the history of its development, the reaction I usually get is one of disbelief and, somewhat ironically, skepticism. You can see them thinking one of two things. Either their inner monologue is going something like, "You mean to tell me that we just spent like 3 months learning about something that might not be right?" Or they're asking themselves, how can science not create reliable knowledge? Look at all the stuff that science has given us. This second response is probably the most common response you'll get from people who are associated with science or who are working in science these days. If you think about it, it's a hard argument to counter on a pragmatic sense. Just on this show alone, we've discussed that scientific-based inquiry has produced a broadly correct and compelling picture of the nature of matter, even if there are a few questions about some of the details on the smallest and most esoteric of scales. Additionally, we just finished spending the last 2 years navigating our way through humanity's quest to know its place in an expanding universe. Knowledge that was arrived at, in many cases, by explicitly applying Francis Bacon's method of experimental philosophy, or, as it is sometimes known in philosophical circles, eliminative induction. This is in addition to our ever-growing knowledge of the chemical machinery of the biological molecules that encode and transmit information necessary for life, the growing understanding of the structure and history of living things, the mechanisms of disease and immunity, and the interrelatedness of all of those things in an ecological systems perspective that has emerged in just the last 70 years. And even this doesn't include the growing understanding of deep time and the enormous cycles that drive the processes that shape our planet and its surface features. All of this knowledge has been produced, tested, and in most cases verified by processes founded on the very means that Hume and others have called into question. For many who practice science, the best answer to Hume's problem is to point out the incredible success that scientific processes of inquiry, usually founded on inductive methods, have had in uncovering the mysteries of nature in their myriad forms. Induction has to be okay because induction works. Hume, I think, would have been somewhat sympathetic to such an argument, though, if we think about it, during his lifetime, a period when scientific inquiry had only just begun to emerge fully from the sorts of questions and answers offered by traditional medieval philosophy, there wasn't such a wonderful track record to work from. Just a generation or two earlier, there were still those who, putting forth all sorts of empirical evidence and arguing inductively, were making alchemical claims and suggesting all sorts of other bizarre phenomena such as wound salve and the like. During his life, there were those who rejected Newton's great synthesis of physics and astronomy in favor of the reasoning of Descartes, Leibniz, and the continental rationalists, even as men like Halley and Voltaire and women like Émilie du Châtelet extended Newton's work to produce new concepts such as energy and explain events like periodic comets. The success of science, while perhaps obvious to a few enlightened philosophers, was still a ways off. More importantly, however, there is a more fundamental difficulty with the argument of the success of science. It doesn't actually address either of Hume's core arguments. It doesn't make explicit the reality of causation, still assuming that such a thing as cause and effect actually exists, and it still begs all the same questions. Questions like, why do we think science will produce reliable knowledge? Well, it has in the past. Even if that were always true, something that's not the case if you recall the idea of phlogiston from our second season, there's no guarantee that it will in the future. Newton's assertion of universality is not an empirically demonstrated reality, but rather a claim made by the great thinker in order to better understand and explain past observations. Hence, the argument that science will work in the future, because it has worked in the past, is an inductive one, and thus subject to the same criticisms Hume leveled originally. As crew member and podcaster Steve Guerra wrote me, human beings are often inductively drawing conclusions that turn out to be false. For him, he sees it in the way his youngest students in the first and second grade come to conclusions about how the world works. So often, we work with very limited experience from which to see any relationships we might draw. And this isn't just limited to the young or inexperienced. Our minds are profoundly geared to seeing connections. Just because something happened in the past doesn't mean it will occur in the future. I mean, how many baseball players wear the same pair of socks without washing them because they broke out of a hitting slump when they forgot to throw that pair in the wash one day? Aren't all of our superstitious beliefs really based in incorrect induction and folklore combining to create a system of risk avoidance? So, if the success of science can't be used as a philosophically valid argument for the reliability of the knowledge arrived at through scientific inquiry, are there means by which we can make such a case? In this episode of the Scientific Odyssey, we'll consider a few others and evaluate them for both whether they provide an answer and to see what they tell us about the process of scientific inquiry itself. Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a mini-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Series 4, Science and Certainty. Episode 2, Hypothetically Speaking. As is so often the case when you talk about David Hume and his philosophical work in a historical context, the next figure that comes up is usually Immanuel Kant. Now, we're not going to get into the fullness of Kant's writing on science and scientific knowledge, as that would take us many additional episodes to really explore. But I do want to drill into one idea that he had, known as a priori truths. So, what is this thing, an a priori truth, or a sort of before you know kind of truth, according to Kant and what he writes? Well, this is something that the universe has to have in order to be a universe. For example, we know a priori, or at the outset, that there must be such a thing as matter in the universe. If there's a physical universe, the stuff in it has to be made out of something. We might not know what the nature of that stuff is, but we do know that it has to be there. Another thing that might fit into this category might be space, something for the matter to move through. Now, for the purposes of our narrative, one of the things Kant wants to lump into this sort of group of types of things is causality. It's something that has to be an a priori thing in the universe. There have to be interactions between the things in the universe, or else we would never be able to detect them. And so that means there has to be some sense where one thing has to cause another thing, or what we would call cause and effect. This, for Kant, is established via deductive reasoning, working from the axiom that there is actually a physical universe. In this sense, Kant is therefore arguing against Hume's first argument that causality is only assumed from continuous conjunction, i.e., when A, then B, in all observed instances. Or, to use our example from our last episode, if I turn the steering wheel left, the car turns left in every instance. Kant's argument is to say that cause and effect is really there, even if we can't directly observe it, and that our continuous conjunction is a result of that which always exists. This turns out to be a really important argument for the following reason. What Kant will build from these a priori ideas is that the universe can be thought of as being what we would call quote-unquote lawfully uniform. In other words, the universe isn't some willy-nilly thing where the rules of how it behaves change all the time. Matter is a certain type of things, and it behaves according to specific rules or laws or interactions. The same is true with space, or later maybe space-time. So too, causality. Again, we may not know all of the specific details of these rules, but whatever they are, they don't change because they can't, and still have a universe that we live in. An example of this kind of thing might be a game, say chess. Now, let's do a thought experiment, something like we did last time, and let's say you've never played the game, and you don't know the rules or anything about it, but you were told that the secret to life and happiness and everything else depended on you coming to understand the game. What would you do? Well, you probably start watching examples of people playing the game and begin to try to figure out what rules govern the game. You'd probably pick up pretty quickly that one of the rules is that the players have to take alternating turns making moves. Then you'd see that each player can only make one move per turn, and that a move must consist of moving one and only one piece of a single color. And by the way, for the chess players out there, I know that there is a circumstance where that rule can be violated, but a brand new observer might not see this at first, or even for several games, depending on which ones he or she gets to watch. At some point, you'd see a player make a move where one of his pieces took another piece of the opposing players, and so you can conclude that pieces can capture others, but there are probably rules for how that happens. You'd soon inductively figure out that differently shaped pieces move in different ways that are constrained or limited in certain aspects. Now, at no time would you quote-unquote know what the actual rules are, but you would know a priori that the board has a certain size. There are a certain number of pieces, and those pieces moved on the board in discrete ways, say in quantum steps, according to very specific rules. You have to have those things to have a game. There has to be a board, there have to be pieces, they have to interact. This is what Kant is getting at in his ideas regarding the universe. We may not know what all the rules are, but we know there have to be some, just as we know there have to be pieces in a board for the universe to play on, so to speak. This lawful uniformity therefore does away with Hume's argument that just because something's happened in the past doesn't mean it's going to be that way in the future. Kant says that such uniformity is an a priori reality required for there to be a universe that rational beings can be in and can understand. In other words, like I said before, you have to have the board, you have to have the pieces, and you have to have causality, or you can't have a game that anyone will be able to play. Now, I'm not sure Hume would buy that argument, but it does answer some of his objections in a reasonable fashion, I think. What Kant's argument doesn't do, though, is to say that induction is always going to produce 100% reliable knowledge. Remember back to that thing that we were talking about when we were talking about moves in the game. There is a move called castling where you actually get to move two pieces in a very special circumstance. Watching the game, using inductive reasoning from what you've seen, you might not catch that that's an illegal or allowable move if you don't actually see that in one of the games you watch. And so your inductive knowledge might not be 100% reliable or 100% complete. The reason for this, as Kant readily acknowledges, is that induction can be wrong in its application of a principle from a limited set of examples to a general rule, and then, to extend that in the way Grosseteste did in the Middle Ages, apply that general principle back to a new specific instance. To use a different example from last time, you observe 1,000 white swans in Europe, and you find every single one of them to be that same color, or all colors, I guess, of white. You then make that inductively based argument that all swans are white. That's induction going from specific instances to a general principle. Next, your friend asks you that if you were to find a swan in Australia, what color would it be? In going from general principle to the specific instance, of course, you would say white. Unfortunately, if you were looking in the southwest part of that continent, there's a good chance you'd find a black swan, thus invalidating your inductive argument. Kant is okay with saying that induction does allow for that, and is thus not always going to produce reliable conclusions in the absence of direct observations in the way that deductive reasoning will. However, what Kant does argue is that a person can be reasonably justified in believing the conclusions that have been reached inductively. To put it another way, a person would be reasonable to place their faith, as it were, in a conclusion arrived at in this fashion. The example he uses in his writing is in relying on a particular strategy when making a decision in warfare based on a strategy that has been used successfully in the past. The strategy may not work in this particular instance, but the person that made that decision was not unjustified or irrational for using the strategy given its previous success. This gives Kant a second argument for the justification of using an inductively based scientific approach to understanding the natural world in opposition to Hume. Even if the principle of uniformity can't be defended deductively, that doesn't mean that knowledge arrived at assuming that principle is unjustified. Kant says that Hume is, in a sense, creating too high a standard when he says that the only knowledge a rational person can rely on is that which meets the same standard as deductive reasoning or deduction. Instead, one can be rational if one assumes these certain a priori conditions for there to be an understandable universe and then work from there, including the assumption of things like causality and uniformity. Note again, Kant doesn't think causality is an assumption, but rather something that can be established deductively. But even if that weren't the case, a rational person can be justified in working from it. It is in this way that Kant argues that science is able to produce knowledge that one may justifiably believe, even as he acknowledges that induction does not meet the same standards as deduction in producing certain knowledge. So, if the 18th century was the century of Hume and then Kant, what's happened with the problem of induction since then? Well, there are a couple of threads that we can kind of follow into the 19th century and then into the 20th. The first has to do with those who carried on the Kantian flags, such as Hans Christian Ørsted and others like him. These writers, often practitioners in the physical science, focused on the idea of Kant's drive towards a synthesis of scientific ideas around the various a priori concepts that would be discovered through empirical means. As such, there was a distinctly unifying nature to their views and their work, as evidenced by Ørsted's work in showing the link between electricity and magnetism that would be an important forerunner to that of James Clerk Maxwell. This dovetailed nicely with the European rationalist tendency to create what might be called hypothetical or theoretical systems of explanation for various natural phenomena. Example of this can be seen in Lagrange's reformulation of Newtonian mechanics in terms of overarching concepts such as energy and momentum, as opposed to the much more tangible forces in nature approach the Englishman had taken in his Principia. This led to the second movement during the 19th century, and that was the struggle to define what process scientific inquiry actually followed or should follow. The two primary voices in this debate were the British philosophers John Stuart Mill and William Whewell. For our purposes in this episode, the details of their debate aren't as important as some of the ideas regarding how science was done that Whewell brought up. To summarize the gist of things very quickly, by the 19th century there was thought to be, among some, a crisis in science. It was sort of thought that whatever vital energy or impetus that had propelled the great minds of the scientific revolution to develop an entirely new method of inquiry, that energy had been lost, and that a new, more deliberate effort had to be initiated to rediscover what had created the conditions necessary for the great leaps forward. To do this, Whewell, along with three colleagues at Trinity College, began to talk about what it meant to quote-unquote do science in much the way that Francis Bacon had done back in the 17th century. As an aside, I should probably find time to do a supplemental episode on Whewell and his career as a polymath that intersected with the lives and work of so many other thinkers of his time. In England at the time, there emerged sort of two strands of thought regarding this whole question. One, advocated by Mills, said that scientists should sort of double down on Bacon's inductive methodology. They argued that in the intervening couple of centuries there had been an encroachment of the various biases that Bacon had warned about in his writing, what he called idols, and that science would once again begin to progress more rapidly if there was an explicit attempt to return to only allowing what could be directly observed with the senses and the use of any relationships that could be established therein. Some of the more ultra-empirical views went so far as to say that only those relationships that could be directly observed in nature happening in a particular time should be accepted as having any validity. In this way, they would also sidestep the problem of induction by only reporting those empirical matters of fact. Critics rightly argued that such an approach would be far too restrictive, as, for example, one would have to reject Newtonian gravitation as a valid scientific idea, as gravity is of course unobservable in a direct sense, and thus the motions of both falling objects and planets around the sun would be robbed of an explanation. Whewell, on the other hand, offered a much more attractive model of scientific inquiry that, while still grounded in inductive empiricism, allowed for other factors to come into play. He asserted that within the practice of doing science, there was, as he called it, a quote-unquote fundamental antithesis, where there were sort of two sources of knowledge. One, the objective, that came from observing the natural world, and another, the subjective, that came from the mind of the investigator or inquirer, based in part in how that person saw or perceived the natural world they were exploring in terms of their own mental frameworks, something that he called their fundamental ideas. And we'll come back to this fundamental ideas thing here just in a moment. In this view, Whewell criticized Mill and others for being too inductive and focusing too much on the objective facts, while also holding to the view that Kant was too focused on the more subjective, as Whewell saw it, a priori ideas in his discussion of how science should be done. I think that the best way to understand his approach is to begin with an example and then work from there. In his writing, Whewell discusses how it is that Kepler arrives at his laws of planetary motion. As we discussed at some length in Season 3 of this podcast, Kepler inherited a treasure trove of data regarding the positions of the planets in the nighttime sky from Tycho Brahe. In empirical terms, Brahe, provided all of the facts, and he had them all at his disposal, but he couldn't create a coherent framework in which to place them. Thus, he hired Kepler in order to make use of his mathematical talent to create what we would call a model today that would account for these motions. Kepler, over a bit of time, was able to work from the idea of circular orbits to create a model for the orbits of both Mars and the Earth that were characterized by the mathematical figure known as an ellipse that would account for the observation of Mars's position in the night sky on the dates and at the times those observations had been made by Tycho. Now, the key idea here is that Kepler's eventual decision to model the planetary motions with elliptical orbits around the Sun, something that he arrived at after great toil and not just a few mistakes, was not something he could have ever sort of seen or had suggested to him empirically. There was no way he could have directly observed that kind of motion or somehow seen the planet moving in an ellipse. Instead, he had to, by inference, use an entirely hypothetical figure, something that came directly from mathematics that he might never have actually seen in nature, though, he probably had drawn any number of approximations of an ellipse in his time as a teacher at Graz. Once he arrived at this hypothetical figure for the orbits of Mars and the Earth, he was able to predict where Mars would be seen in the sky on future dates. In essence, being able to move Mars forward along its orbital path, while at the same time doing the same thing with the Earth. Moreover, believing that the hypothetical figure that applied to these two planets in a heliocentric configuration must apply to all planets, both known and as it would turn out, unknown, he was able to apply it to their orbits as well, eventually deriving the first two laws of planetary motion. So, to move from specific to general, much as Whewell demonstrated Kepler had done, Whewell said that science is often done in this very same way. Rather than basing all ideas and descriptions on only empirically arrived at information, there are times when the scientist will start with data, a collection of observational facts, and then apply some sort of framework from outside of the empirical evidence to the data to make sense of it, or, to put it another way, find a pattern, model, or theory to account for those observations. What is key in Whewell's description here is that the source of this pattern can come from a number of other places. It can be inferred from previous similar experiences, it can be matched to mathematical patterns, it can be based on a hunch or some intuition. What's important is that the generalizing framework does not always have to arise from purely, or in some cases even remotely, empirical considerations. Perhaps one of the most striking historical examples of such a thing is the intuiting of this structure of benzene by the chemist, and I'm going to mess this name up, I'm sure, Frederick August Kekule. Now, some of you may know the story, but Kekule was an important figure in the development of the theory of chemical structure based on the idea of atomic affinity units, or what we now call valence, working specifically with carbon and its ability to bond 4 times in various configurations depending on what the other elements were that it was bonding to. As a part of that work, Kekule was attempting to understand how the carbon atoms in benzene were organized, and in 1865 he published a pair of groundbreaking papers, one in French and the other in German, showing the structure of the organic molecule to be a hexagonal ring with carbon atoms at 6 vertices and having alternating single and double bonds. And if you don't get that, don't worry about it. The chemists out there, you'll totally be down with it, I'm sure. The important thing is that on the 25th anniversary of this discovery, the German Chemical Society organized an anniversary celebration, and at the event, Kekule related that he had been inspired to investigate this structure on the basis of 2 dreams that he had had. Now, for the sake of completeness here, the sources that I've been able to consult for this whole thing are a little bit contradictory in whether these were actually just daydreams or if they were really actually sleeping dreams. But whichever was the case, in the first dream, Kekule explained that he had visualized the carbon atoms dancing around and linking to each other. When he came out of the dream, either by waking up or rousing himself from his reverie, he sketched his visions for further consideration. Shortly after this, he had a second dream, and in this instance, the atoms once again began to dance around and link up, but in that case, they formed first into strings that then began to move around in a snake-like fashion. Soon, during the dream, one end of the string began to circle around behind the others, and the strings became snakes that caught their own tails, imitating an ancient symbol of renewal known as the Uroboros. Again, upon coming to, Kekule realized that the carbon atoms would not just form long chains, but would structure themselves as rings, a structure that would soon be shown to be the correct description of the benzene molecule. Now, it's really hard to explain this kind of a process of coming up with this sort of an idea using any sort of an inductive mechanism. I'm pretty sure that Francis Bacon wouldn't have known what to make of Kekule's experience in terms of his description of the process of scientific inquiry, but for Whewell, the use of human imagination, intuition, and creativity has had just as central a place for hypothesis formation as any practice of repeated observation of nature to determine what patterns might be noticed or present when examining any sort of a phenomenon. What's really interesting here, at least for me, is that Whewell also explicitly states that the a priori concepts of Kant will frequently serve as sources for hypothetical frameworks. And while there are some important differences between how Kant sees these things and the way in which Whewell characterizes his similar but somewhat different fundamental ideas, doing this allows him to appropriate, in a sense, Kant's response to the problem of induction, something seen as being necessary by many who sought to confirm the validity of any sort of scientific practice. Just as importantly, Whewell put forward the idea that these fundamental ideas, things like space, time, substance, shape and influence the kinds of observations all scientists make. In this view, as these ideas were encoded into the human intellect due to the fact that they were part of a reality created by a supreme being, meant that they were useful guides, at least as far as Whewell saw them. In postmodern philosophy of science, the idea or theory-laden nature of observation is held to be a form of bias in a process that is socially constructed. While there has been some well-argued pushback against this idea of being foundational to scientific inquiry, even the most empirical scientist has to admit that the way in which we think about the world frames how we choose to investigate it going forward. At this point, however, we once again risk going off on a tangent that would consume several episodes, and actually might somewhere down the road, and so we'll just leave that there for the time being. Now, according to Whewell, once the hypothetical structure has been arrived at, by whatever means have been used, then that hypothesis has to be able to make predictions about the behavior of the system in future instances. In the case of Kepler's laws, they had to be able to tell you where to look for Mars or Saturn or whatever in a given year, or on a given day, or on a certain month. This was, in fact, the reason Kepler published the Rudolphine tables, as a way to help the less mathematically inclined astronomers know where the planets would be in the future. That his predictions turned out to be so stunningly accurate, especially compared to the ephemerises of earlier astronomers such as Ptolemy, Copernicus, or Tycho, became proof for many of the validity of his elliptical heliocentric model. In the same way, Whewell suggested that when the predictions of a hypothetical structure are confirmed by later empirical evidence, the hypothesis, whether it be labeled a law or theory, would be held to be conditionally true. Whewell describes this process as something that happens in 3 steps, or tests as he calls them, which are known as prediction, consilience, and coherence. For the first, Whewell says that, quote, our hypotheses ought to foretell phenomena which have not yet been observed, end quote. In the second case, that they should, quote, explain and determine cases of a kind different from those which were contemplated in the formation, end quote, of those hypotheses. And finally, that the hypotheses must, quote, become more coherent, end quote, over time. As we've already discussed the importance of prediction, let us take a moment to move to the other 2 tests of a hypothesis. The second test, consilience, Whewell sees as being more valuable a test than prediction. As he writes, quote, the evidence in favor of our induction is of a much higher and more forcible character when it enables us to explain and determine cases of a kind different from those which were contemplated in the formation of our hypothesis. The instances in which this have occurred, indeed, impress us with a conviction that the truth of our hypothesis is certain, end quote. In other words, a hypothesis is to be considered more empirically accurate if it can explain not only the things it was originally designed to account for, but also other systems that might be similar but in some way different than the original. A good example of this we might consider is Maxwell's kinetic theory of gases. As we discussed in our last episode, there is something known as the ideal gas law that could explain the behavior of certain types of gases, that had certain basic characteristics. But the problem was that law didn't account for why the relation itself worked and why it only worked for those kinds of gases. When Maxwell takes that data and places it into a statistical theory based on the movement of a very large number of atomically based molecules, he is not only able to derive the ideal gas law, but also a much more general expression that can be applied to any gas, and even, in some cases, to liquids. His kinetic theory shows a strong amount of Whewell's consilience in being able to address all sorts of different kinds of gases. A similar thing can be said of Newton's universal law of gravitation and its ability to explain the motion of all celestial objects in many different cases, not to mention tides, falling bodies, the shape of the earth, and other phenomena as compared to the much less versatile laws of planetary motion put forward by Kepler that only explain the behavior of a very small class of objects, i.e., things that directly went around the sun. The final test of a hypothesis, or hypothetical explanation, is that of coherence. As Whewell wrote, quote, the system becomes more coherent as it is further extended. The elements which we require for explaining a new class of facts are already contained in our system. In false theories, the contrary is the case, end quote. The best example for this, I think, is atomism or atomic theory. One of the strongest arguments for an atomic theory of matter is that it can be used to explain a number of diverse physical phenomena without having to add any sort of details to the theory. In addition to explaining chemical reactions, it was used by Maxwell to understand gas behavior, as previously mentioned, and it would be used by Einstein to explain Brownian motion. That the theory can do all of these things without having to be modified in a significant way gives it, as Whewell might put it, an empirical credibility above those fundamental ideas that do not. As a final piece of Whewell's picture of how science is done, we have the idea that is first found in a sense in the writing of Galileo, but that Whewell brings forward and makes explicit. And that is, if you have a set of ideas that are, as he puts it, necessarily true, then there can be determined other things that must also be necessarily true from those ideas. In other words, once you sort of have a set of ideas, you can use deductive reasoning to draw conclusions from those ideas or theories that must also be true. In Galileo's writing, the idea is that once you represent physical laws in mathematical form, any result you can derive by manipulating the mathematical equations can be thought of as actually being the case in the real physical world. An example of this we use in my introductory physics classes is the development of the idea of conservation of momentum from Newton's laws of motion. This result can be shown from a fairly straightforward calculation, and so, according to first Galileo and then later Whewell, we can take the result of the calculation, i.e. that a quantity of momentum in a system must remain constant in the absence of a net external force, as a necessarily true statement. If this were not the case, then that would mean that we miss some important part of the system's description, and thus, in a deductive sense, one of the premises that we've included in our system's description must be false. To wrap all of this up, at least for a moment, let's summarize Whewell's two most significant contributions here. First, he asserts in a convincing way the view that scientific investigation is not merely an empirical or purely inductive exercise, but rather one that brings in another element, those fundamental ideas an investigator might possess to add to his hypothesis formation. Secondly, he introduces the claim that there are deductive reasoning processes at work in scientific inquiry that must be acknowledged as valuable in making progress towards a better understanding of the natural world. And while he does not provide a more satisfying resolution to Hume's problem of induction than Kant did, he does illustrate a much fuller and more nuanced picture of how science was actually done. As we move into the final part of our discussion in this episode, I want to take a moment to tread where only the foolhardy go for just a moment. One of the debates I've run across in my readings on this topic in the area of history of the philosophy of science is whether Whewell was the first of a group of philosophers of science who put forward something known as the hypothetico-deductive method. We'll talk about that more down the road here in just a few minutes. For some, the answer is an unambiguous yes, and they see a line that can clearly be drawn from Kant through Whewell's work to the ideas of the Austrian philosopher Karl Popper, about whom we shall have much to say here in a bit. For others, such a claim is represented as ludicrous, as they note Whewell's criticism of some of Kant's ideas and his repeated insistence on the fundamental nature of empirical data as the foundation of all scientific thought. This school of philosophical or historical philosophical thought places Whewell solidly in the British inductivist tradition, working from Bacon through Newton and Hume to individuals like John Herschel and John Stuart Mill. So, which is it? Well, as will likely not surprise those crew members who have been under sail with us here for a while, it is our very amateur opinion that this is yet another example of the seemingly endless number of false dichotomies scholars so often engage with that tend to sort of obscure the truth. From what I've been able to learn, it seems likely that Whewell would have included himself in the inductivist tradition while also serving as an important bridge out of it. Whewell very much saw himself and those he worked with as attempting to revitalize the inductive method of Francis Bacon. However, I think it is also fair to say that he realized that doubling down on that method was unlikely to provide the new energy he felt was needed to kickstart what he saw as the flagging enterprise of scientific practice. For him, there had to be new ideas and new understandings, one that Kant and his proponents seem to have hit upon in their writings on both scientific inquiry and on nature itself. As such, I think it's safe to say that Whewell is both an important bridge from pure inductivism to something more complex and richer, and also a unifier of the best ideas and practices of those who had gone before him, including ideas of Bacon, Galileo, Newton, Hume, and Kant. When scientists talk about the practice of doing science today, what you tend to find is that they are most often likely to give a description that is, by and large, congruent with Whewell's work. If there is to be a single description of the scientific method, or a scientific method, and by the way, I'm among most philosophers of science I know of that, say that probably such a thing as a single scientific method doesn't exist. But if it were to be that kind of a thing, it's probably Whewell's version with perhaps a few modifications or additions. The interesting thing for our discussion here is that Whewell's description of scientific inquiry still does not fully address Hume's problem of induction, something that Whewell probably wasn't all that concerned about. It still acknowledges that scientific knowledge, while justified, cannot be completely certain. As the 19th century moved towards the 20th century, a number of philosophers of science found this to be disquieting. Even as science was beginning to have some real success in understanding the natural world that was hidden from direct observations in fields like physics and chemistry, these philosophers found themselves deeply uncomfortable with several aspects of scientific practice and the assumptions about scientific knowledge. This uneasiness was not limited merely to the reliability of scientific knowledge, but also extended to issues with theory-making, whether those unobservable aspects of a theoretical construct could be considered as real, and how one might distinguish areas of study that were truly scientific from those who only seem scientific on the surface but lack the requisite criteria to be truly included in those disciplines, things that most of us call pseudosciences today. As modernity came about in the broad culture, so too did a new impetus to address many of these problems in scientific inquiry. This became especially important after the development of both the quantum and relativity theories, each of which called into question the reliability of observationally defined concepts such as space, time, determinism, and measurement. For our discussion, the problem of induction was once again taken up, but this time the approach was to claim that science did not, in fact, use induction as a fundamental basis for arriving at knowledge of the natural world. In the 1920s, several related approaches were suggested by philosophers such as Karl Popper and Jean Descartes that held that scientific knowledge consisted of a series of formal logical statements, sometimes called hypotheses and other times referred to as theories. These logical statements were arrived at, it was claimed, through a non-inductive process or set of processes that, while sometimes rooted in empirical data, were actually the product of human creativity and intuition, processes that were thought to be decidedly non-inductive. As an example of this, let me describe to you a game I play with my students in a couple of my classes known as Petals Around the Rose. In this game, a person who knows the secret of the game rolls 5 standard 6-sided dice after telling the players that the only hint they are to be given is that the answer to the question, how many petals around the rose are there in this roll of dice, will always be an even number. The person or people playing the game then predict the number of petals around the rose, to which the person doing the rolling responds by telling the player if they are correct or not, and then gives them the correct number of petals. Now, while the die rolls are empirical in nature, it is thought here that the process of hypothesis formation in the mind of the player is not an inductive process in nature, but something else. So let's get this actually down to, something more realistic. Let's say you and I play the game. So I'm going to sit down, I've got 5 dice, and I'm going to roll those. And then let's say I roll the following 5 die faces, a 2, a 3, 2 5s, and a 1. And now what you have to do is you have to come up with a way to arrive at a conclusion or a prediction about the number of petals around the rose. Now, let's say you decide or you predict the number to be 16. And you do that based off a hypothesis that you've come up with that the answer to what is the number of petals around the rose is determined by adding up all the dots on each die face. So you're going to add up 2, 3, 2 5s, and then a 1 to get 16. You came up with that a hypothesis not on the basis of any previous experience, you never played the game, but through the use of your creative imagination as applied to this particular system. When I tell you that the correct number of petals around the rose is 10 rather than 16, you'll have to revise your hypothetical framework, a process that is again creative nature, in order to make a new prediction after I roll the dice again in the next round. And by the way, if you're now intrigued by this game, and how can you not be, I should tell you that I'm not really going to give away the rules of how the correct number is arrived at. There are rules, and they're very specific. But I know them, and you don't. Kind of like when a scientist is trying to understand the universe. The universe knows the rules. The scientist doesn't. The scientist has to figure that out. If you're interested, though, in trying this out, you can go online, and there are a number of simulations that will play the game with you. Perhaps after listening to this podcast episode, you can give one of them a try and see if you can come up with the secret to the petals around the rose. Okay, so let's get back to the big picture stuff here. This description of doing science is known as the hypothetico-deductive model or method of doing science. The first part of this title comes from the creative hypothesis formation process that we've just illustrated. The second part of the title comes from what's supposed to happen next. Once you have a hypothesis or a theory that describes nature, you then, and by the way, we're going to go ahead and use the term theory henceforth just to make things simpler. What you do as a scientist is you come up with as many consequences of your theory as you can deductively arrive at. Say, if the hypothesis or theory is Newtonian gravity, then those consequences are things like the motion of freely falling objects, the orbital paths of celestial objects, tides, the shape of the Earth, a whole bunch of stuff. In chemistry, it might be the predictions of different types of elements and how they bond with other elements based on valence numbers or electron configurations. Whatever the theoretical system you're working with, these deductively arrived at consequences are then tested, experimentally if possible, and observationally if not. If the theory is shown to correctly predict the consequences, then the theory is conditionally confirmed. But if it is not, then the theory is shown to be deductively false, as there must be a problem with one or more of the fundamental axioms or premises of the original theory in order to have made an incorrect prediction. In this way of thinking about science, the problem of induction is solved by removing induction as a logical tool entirely. Descriptions of nature are arrived at creatively and then tested deductively, and so there really is no inductive process occurring. This school of thinking also addresses Hume's concern in another way. When Hume talks about induction, he's really discussing a kind of induction that we call a numerative induction. In other words, the creation of causal relationships between two things or events based on repeated, over and over, continuous conjunction kinds of things. Turn the steering wheel to the right, the car turns to the right, over and over and over again, until you associate the two in a cause and effect relationship, even if you can't directly observe the causality. What a proponent of the hypothetico-deductive method, or HDM for short, and that's what we'll call it from here on out, will point out is that most of what we know in the modern world is known as part of a much more complex set of connections. In other words, if you're clever, you can open the hood of the car or get underneath it and find all the mechanical linkages from the steering wheel to the front axle of the vehicle that causes the wheels to turn when you turn the steering wheel, right? Same thing when we talk about nature. While there was certainly a time when we assumed the sun would come up tomorrow, because it had done so for as many days as human beings had been paying attention to that sort of thing, most of us, when pressed for an explanation of this, will be able to talk a bit about the Earth rotating on its axis and such. Those with a bit more education in the sciences can probably trot out a very complex set of interconnected hypothetical statements based on something known as gravity that will explain the orbital dynamics of the Earth's motion through space and its orbit around the sun and a whole bunch of other stuff. These hypothetical frameworks, claim the HDM folks, are products of human creativity and imagination, as we said. Newton never observed gravitation, nor Einstein curved spacetime. Until the launching of satellites and space probes, no one had directly observed the Earth's motions, either on its axis or around the sun. Instead, these were conceived of as intellectual exercises based on what had been observed in the past and thinking up new ways to explain them. The validity of these theoretical frameworks were established through experimental or observational testing of the new predictions that they made. Complex induction, as claimed, is not subject therefore to Hume's problem because it rests on a much firmer foundation than the type of induction that Hume had discussed in his work. Now, before we address this model, we need to look at a final extension of it put forward by the Austrian-born and educated philosopher Karl Popper. I'll likely do a biographical supplement on Popper somewhere down the road a ways, but I think it's safe to say that he is in the running for one of the most influential philosophers of science in the 20th century. Part of the Vienna Circle for a time, Popper had fled Austria with the rise of fascism and landed in Britain, where he wrote on a number of topics, including the defense of democracy, that is suddenly and surprisingly relevant today. In his work on philosophy of science, what he wanted to do was create a strong delineation between what he called science and pseudoscience. That's something that we usually call a demarcation criterion, as a way to refute much of the ideological posturing that was passing itself off as science during the 1930s. As a way of doing this, he proposed the idea that science is best done when it puts forward bold and unorthodox predictions that can be clearly falsified through well-designed experiments. For our narrative here, the strength of this falsifiability criterion, as it was called, is the following. If we think of a theory that makes a certain claim, say that all planets will orbit the sun in ellipses, as Kepler's first law of planetary motion does, once you've found about half a dozen or so planets that do this, finding another one doesn't really do much to strengthen the likelihood that your theory is correct. What Popper says is that what you need to do is go looking really, really hard, if necessary, for something that will disprove your theory. In this example, go out and look for things that don't orbit the sun in ellipses. Maybe they're going to orbit the sun in circles, or parabolas, or hyperbolas, something like that. If you find one, your hypothesis is then disproven and thus can be rejected. For Popper, the prototypical test of this sort was Einstein's prediction of the bending of the path of starlight that traveled close to the sun. There were just a couple of clear-cut possibilities for this experimental outcome. You could get the amount predicted by general relativity, the amount predicted by Newtonian gravitation, which would have been about half of that predicted by general relativity, or some other amount that would say both theories were wrong. In this experiment, carried out, of course, for the first time by Eddington in 1919, and then several times after, there could be no unambiguous results. No sort of squirreling around or, sort of fudging the theory. Either the results confirmed Einstein's general relativity, they confirmed Newtonian gravity, or they said both were wrong. By adding falsifiability to HDM, Popper was, in a sense, strengthening the deductive nature of the method by pushing scientists to seek out hard tests. It is worth noting that ever since he published these ideas, physicists and astronomers have been working very hard to produce tests that can falsify Einstein's general theory. And rarely a year goes by when there isn't some news article relaying, and this just happened here again recently, that once again scientists have failed to disprove it. And note, the verbiage is almost always that, if the news article is written correctly, that the scientists failed to disprove. With all of this in place then, why is it that we don't teach this as the quote-unquote the scientific method and just stop worrying about the problem of induction? Well, as you probably guess, there are a couple of reasons. First, one problem with HDM is that it never actually really proves anything in a deductive way, at least in one sense. Sure, you can prove something wrong, but you can never prove it right using HDM. While it may be the case that those hypotheses that survive the rigorous falsifiability testing of Popper have a much higher likelihood of being correct, you can't actually argue that they are deductively proven. In other words, the theories work so far, but there's no reason to think they won't be shown wrong in the future. In the case of general relativity, the theory has survived all the tests up till now, but who's to say that in a couple of years down the road, some really bright group of researchers won't come up with a test where Einstein's great theory makes the incorrect prediction, the same way that Einstein's great theory did in trying to predict Mercury's orbit around the sun. The other major knock against HDM has to do with its account of hypothesis formation. While it is correct to say that human imagination and creativity play a much larger role than a strong inductivist would usually allow, it's hard to think that anyone really invents anything out of whole cloth. When one looks at the history of science, no individual comes up with things completely out of the blue. There's always some connection back to the ideas of earlier thinkers and researchers who depended on those who came before them. In our billiards example from last episode, even if you've never seen billiards play, it's pretty likely that there was some previous experience in your background, say playing marbles in the schoolyard, you could draw upon that would help you construct a hypothesis as to what would happen when two billiard balls collide. Given the iterative nature of scientific inquiry, that's all one really needs to get started. Hence, as many of its critics have pointed out, while things are more complicated than just observing the world and generalizing the relationships and regularities one sees in the behavior of a given system, there's still a foundation of induction in that process of hypothesis formation. And so, what that means is you haven't really eliminated the problem of induction. Finally, there's one other thing that gets in the way. The HDM process, as we've described it, is not actually really the way science gets done. In Popper's version of HDM, if a scientific theory fails a strong test, it's supposed to be discarded completely. Eddington and those after him observed a shift in the position of the star near the sun during a total eclipse consistent with the prediction of general relativity, and so Newtonian physics has basically been done away with. Period. The end. However, if you look back on the history of scientific practice, that's actually not what usually happens. A good example from this last season was the case of what was going on with Uranus. When the orbit of the planet didn't match up with the Newtonian predictions, throwing Newtonian gravity out was really not most people's first choice. Sure, a few people said, hey, maybe we need to come up with a new theory. But most people said, hey, Newton's been really successful in all of this other stuff. We're not comfortable throwing it out. And so while there were those who suggested making some changes to Newtonian gravity, it was the idea of Leverrier that suggested an undiscovered planet further from the sun whose gravitational influence perturbed the orbit of Uranus that was the thing that sort of found the widest acceptance and that eventually led to the discovery of Neptune. In the case of our model of the atom, and this is another great example, each new discovery hasn't led to a complete rejection of atomic theory, but rather a modification of it. In this way, then, HDM fails to replicate actual scientific practice, and so can't be a fully accurate description of the scientific process of inquiry. So, if that's the case, why is this important at all? Why did I just spend the last, 20, 25 minutes talking about a process or a method that isn't completely accurate and doesn't solve the problem of induction? Well, there are two reasons, I think. First, the whole conversation around the hypothetico-deductive method really does narrow the problem of induction down quite a bit. It shows that enumerative induction isn't really how science works, and so attacking that is a bit of a straw man argument. It also shows clearly that there are other logical elements inherent in science, both inference and deduction, that become important aspects of scientific practice, and where those do accurately describe a part of the process of scientific inquiry, arguments from the problem of induction may not be entirely valid. Second, and this is probably more important, the exercise of coming up with this idea of HDM has taught us so much about how science is really done. And it's here that I'd like to just take a bit more time and maybe go off on a bit of a pining, if you don't mind. In the 20th century, there have been a number of prominent scientific figures who have become frustrated with philosophy in general, to a lesser degree maybe, and with philosophy of science specifically to a much greater degree. Individuals such as Richard Feynman, Stephen Hawking, and Neil deGrasse Tyson have been very dismissive of the role of philosophy of science in its calling into question many parts of the process of scientific inquiry. To be honest, there are times when I have some sympathy with that, when I read those philosophers who would say that science as a form of inquiry had little or no validity, or has little or no validity, that, any number of pseudosciences could be just as valid, even as those individuals who are writing that reap the benefits of scientific discoveries in a nearly uncountable number of ways. However, to be fair, I think the number of philosophers who espouse such radical positions, if I can say that, are relatively small, and many of their arguments have been refuted long ago. When I look at the work of 20th century philosophers of science, what I see by and large is a work that has added immeasurably to our understanding of how science is done and can be done better. Beginning with Whewell and moving forward, the picture of science that involves a strong role for hypothesis formation has been profoundly successful. Popper's Falsifiability Criterion, for all of its shortcomings, many of which we haven't really discussed yet and won't until a later episode, has made for better hypothesis testing in large part. The work of others who we haven't mentioned on things like operationalizing definitions in science have led to a rethinking of a number of assumptions that have led to insights and breakthroughs that are hard to imagine had we merely stayed with the strict inductivism as advocated by guys like Mills. In short, it is my opinion, informed or otherwise, I'll let you decide, that our scientific practice is much improved when informed by the considerations brought forward by philosophers of science. As we reach the end of this episode, let me offer a couple of shout-outs this week, because that's what we've been trying to do. The first I'd like to offer up is I want to shout out to all of those philosophers of science out there that I've just been talking about. We here at the Scientific Odyssey raise a glass to your work, even if we are occasionally flummoxed and frustrated by it. Carry on, good sirs and madams. Carry on. Speaking of raising a glass, I'd like to give a shout out to my colleagues and friends, Doug and Teresa Stanley, who about a year ago were kind enough to buy me a bottle of that most American of adult beverages, Burnside Bourbon, made in my home state of Oregon. And as I record this evening, I am finally finishing that bottle off. It has provided quite a bit of enjoyment over the last year. So, Doug and Teresa, thank you very much. Finally, thank you also to all of the artists, musicians, creators, innovators, the whole bit, who work at the Blue Dot Sessions and who provide the music for these episodes. They come from a number of different things that they have created. They're wonderful composers and wonderful musicians, and this humble effort would not be the same without them. Moving on, for those of you who would like to offer some additional commentary on these opinions and thoughts of mine, I would love to read or hear what you have to say, and so I invite you to leave a comment on our website, thescientificodyssey.typepad.com. On our Facebook page, you can just search for The Scientific Odyssey out there on the book and join the group if you haven't already done so. At my Twitter account, which you can find me at the handle @ChadDavies, or to my personal email address, cldavies@mac.com. Also, even though summer is winding down here, at least here in the Northern Hemisphere, we're still in the midst of our summer odyssey. So if you got pictures or stories of cool science, history of science, philosophy of science, or some combination of the three, please share them at any or all of the previously mentioned spaces. Or if you use the Twitter or Instagram, you can use the hashtags Summer Odyssey, all one word, and or Scientific Odyssey, all one word, and we'll see those. Finally, as you may have noticed, we haven't really addressed the problem of induction yet. It's still sort of out there. So next time, we'll look at a couple of much more recent approaches to the problem to see what they tell us. Until then, full sails on your journey.